I really feel our industry, at least in North America, we're at a critical turning point, and there's a huge divider between synthetics and naturals. And I believe we all have a role to play in that, and education is a key to that role. The more we're educated, the more fluid we are to speak about our technology, then the more at ease technicians and customers will use that technology. So in a sense, we all have our little ambassador hat on, to promote and work with natural refrigerants. And it's definitely the future.
Welcome to the Refrigeration Mentor podcast and CO2 Mondays. This is actually, I've been doing this for 6 months now, having the top guests from around the planet sharing their knowledge with us. If you've been on a lot of these, I've been going back and rewatching them, re-listening to them because there's so much great information. And hopefully you get a chance to watch some of these on YouTube. Please share them with other people so they can see them, because there's a lot of good content. If it's on the podcast, you're listening to the Refrigeration Mentor podcast, please share it on Instagram, Facebook, LinkedIn, so other people can find this content so they can hear from the experts around the world on CO2 refrigeration. This week, I have a returning guest, Phillip Walker from Arneg Solutions, our systems, and we're going to be diving in today into hot gas defrost, as well as how to move heat in a CO2 system. I think we're going to do a recap first of the last time we were together. Welcome, Phillip, to CO2 Mondays.
Hey, thanks, Treasure. Pleasure to be here once again.
I'm so excited about this. This is from the last time we talked. I watched it probably 3 times now on the flash tank stability, because there is just so much gold nuggets in there that I was just picking up things all the time. Every time you listen or re-listen to content, there's little tips and tricks, and I just been loving it. So today I'm really excited to learn more about hot gas defrost in your systems.
Absolutely. So, I got to thank your entire community. I had a lot of positive feedback. I think the idea of visualization with technical discussion worked well for a lot of the folks. Today is going to be a similar format. I know a lot of the folks reached out on how do I calculate that? So I figured, if it flies with the community, we can spend today wrapping up some of this visualization and what this hotcast does. And I'd be more than happy then in a third session to present mathematically, how do you achieve this?
Love it. I love it. Awesome. How lucky am I? This is it. I'm super lucky because I have lots of great people like you. There's many people on the call that's been on the show before and just want to share your knowledge. And you know what? I really appreciate you and every other guest that's been on the show, because you guys, especially in the CO2 community, refrigeration community, we want to share our knowledge and really help more people out there. Because when I was younger technician, I used to be told like all the older people want to hoard their knowledge. They don't want to share their knowledge. But today, everybody I meet want to share their knowledge on CO2. So I really appreciate that, Phillip.
Yeah, I really feel our industry, at least in North America, we're at a critical turning point, and there's a huge divider between synthetics and naturals. And I believe we all have a role to play in that, and education is a key to that role. The more we're educated, the more fluid we are to speak about our technology, then the more at ease technicians and customers will use that technology. So in a sense, we all have our little ambassador hat on, to promote and work with natural refrigerants. And it's definitely the future. The direction going that way.
Yeah, I do. That's why I do this. You know what I mean? This is why I do it, get this knowledge out there. Yeah, so if you want to share anything, or if you want to just dive right into review what we did last time. And
so just for the audience, what we're going to do a quick recap of what we talked about last time in the same format, visualizations with technical discussion, and then we're going to lead into hot gas defrost on a booster side of the system. So using the subcritical side, in this discussion, we'll discuss subcritical hot gas defrost. So I'll share my screen.
And those who are listening on the podcast, will do our best to explain the visual cues.
Okay, can you see this?
Yep.
Perfect. So I'll try and explain much better than last time. I know some of you folks reached out and said, hey, can you explain some of the photo, because I'm listening remotely. So we're looking at a flash tank, and the flash tanks come in various shapes and sizes. What really determines the flash tank capacity is how much flash gas you have, or liquid being the liquid used for the cooling medium, more or less in the system, moving throughout your entire refrigeration system. So this specific one we're going to use for our hot gas discussion today. So at the very top, we have 2 inlet connections. That's for our flash gas. And then in the middle, we got this inlet connection. That's our liquid coming back from the gas cooler. And at the very bottom, we have 1 liquid supply outlet that feeds our liquid header. And on the very top of the tank, obviously, we have our relief connection, which is typically between 650 to 750 pounds, depending on what type of application that we're working on. And all on the side, we have various design PSIAs. This just gives an outline on where Arneg systems is in terms of flash tank pressure in different type of supermarket and air conditioning applications. What we're going to look at today is basically supermarket HG1, meaning hot gas 1, 480 psi, and supermarket hot gas 2, 498 psi. And I know some of you folks reached out and said, what is the big difference between the two? It's really the location of the mechanical room. When we're in a basement and the machine is lower than the evaporator, our flash tank will operate at a higher pressure. And when we're in a mezzanine above the evaporators, we'll operate at a lower pressure. That's the only difference. And as we mentioned here, HG1 evaporators below pack or HG2 evaporators above pack. Okay. So to continue from the discussion we had last week, here's the inlet we were talking about into the flash tank. This is a high pressure expansion device. What we're looking at right now is the middle of a flash tank, and we have a high pressure expansion device. This one happens to be the Sporlan GC series of valves. This over here would be the inlet from the gas cooler, where that transcritical fluid is coming back and it's going to get flashed through this high pressure expansion device. Hence why we have flash gas. Flash gas is a naturally occurring throughout any type of metering device. So your synthetic refrigerant TXVs, your evaporators are going to have some of that gas traveling on top of the liquid. Or in terms of a CO2 system, it's just we have all mass going through this valve. So we have a larger quantity of this flash gas occurring. The reason for the inlet in the middle is because we want that liquid to come in, drain or drip down to the bottom. It's going to, under the pressure, condense, liquid fly, and then drip down and into the bottom of the tank. And that flash gas, being that vapor, is going to naturally rise and naturally rest here at the top of the tank. And this is really, really important for hot gas, because we're going to get into is how that hot gas is coming back to the tank. It's going to interact with the flash gas that's naturally occurring here in the top of the tank. So I'll keep motoring along. So here is a typical setup with subcooling. We have our flash tank that we're looking at right now. We have our high pressure expansion device. We have a secondary high pressure expansion device. This is very typical to our designs. This is one of the most critical parts in an entire system. So we always add a second one. The reason for that, in the event of any failure, it is a mechanical valve, basically, or an electronically controlled valve. It can fail. The advantage of having a secondary valve is you literally unplug this one, you plug the cord into the second one here, and the control system takes right on over while you're waiting for replacement here. We've started doing this over the last 18 months and have had huge success. We've avoided some unnecessary occurrences that could have warranted a disastrous situation in the field upon failure of the valve. So over here, it's just a subcooling coil we spoke about. How are we subcooling? Gas cooler outlets coming through the subcooling coil. We're leaving that subcooled liquid, or somewhat more desuperheated liquid in a transcritical state, flashing through that valve. Once again, liquid being formed inside the flash tank, and liquid is pooling in the bottom of the flash tank, liquid's leaving here, and then we have our flash gas on the very top. So here's our flash gas setup. So obviously we have this gas occurring on the very top of the tank. What do we do with it? Well, we're going to feed in a booster system our medium temperature header. And this flash gas is very, very cool. And there's a few interesting strategies you can use it in the industry, such as subcooling. That's something that we use it for. We even use it to help deheat or desuperheat certain components within large machines. But In an instance, as we have a 500 psia flash tank, the flash gas is at a temperature of around, 30 to 32 degrees Fahrenheit. Fairly cool. So fairly useful for other means than just driving it into the medium temperature suction header. But in this application, pretty straightforward, because we're going to talk about hot gas and then why this is so critical. So this valve here is an electronically controlled valve. It's going to modulate to maintain the pressure inside this tank. This is critical because the pressure inside this tank works directly with the outlet from the gas cooler, which gets, as we spoke about, flashed down through that high pressure expansion device that forms liquid inside of our tank. So remember, throughout transcritical operation, this tank is our condenser. The gas cooler outside is literally doing that. It is cooling our gas, significantly desuperheating that gas, but the final condensation throughout transcritical operation is occurring within this tank. And that's crucial for a hot gas cycle, because we're not going to be returning back to that gas cooler in this instance. We're going to be returning back to this flash tank. And then here's the whole setup. So in the previous episode, we really spoke about every single one of these parts in greater detail, and this was the final assembly. So I really enjoy the visual of slowly putting this together. It really helps us piece this puzzle all together, and we have a better understanding of all our individual components. All this is necessary when we start talking about hot gas. So we have our flash tank, high pressure expansion device, our flash gas bypass valve here. Here's that subcooling coil, gas cooler inlet right here. And then over here, we have our suction manifold for the medium temperature. And right now, that leads a good in-way into our hot gas cycle. So let's jump right into that. Here's a really common diagram. This is a courtesy of Parker Hanovan. I believe most of you folks have seen this in Flowcon magazine or whatnot. But the same theory still exists for a CO2. Once again, we're going to talk about using the booster side, being these compressors right here. For us, it's scroll compressors we use on the low temperature side as a means to provide hot gas defrosting. So we have our booster compressor here, or our low temperature compressor. Here's our discharge line. Now, the amount of heat that you're going to have off of this, remember, we're discharging into the medium suction header. So our actual CR ratio, or our overall compression ratio, is very, very minimal. It's highly efficient. We're going to be condensing of around 28 to 29 degrees Fahrenheit. So if we're running this at minus 25, condensing at 28, 29 degrees Fahrenheit, it's not a huge compression ratio. So the amount of heat that we're generating isn't going to be around 200 degrees Fahrenheit on the booster side. We're more typically around 150 to 160 degrees Fahrenheit. Okay. Now you can say, well, if synthetic refrigerant, we're used to the days of having, 180 to 200 degrees Fahrenheit. Absolutely. So the trick with using a booster side or a subcritical side for your hot gas is really mass. Mass is crucial to your overall success of your hot gas defrost. And I imagine a lot of you folks have heard the stories of, certain defrost times exceeding electric defrost, or, just being not practical for your application. What I'll explain is there's a few tricks out there if you're using the booster side for your hot gas. And you can really help get those defrost times down and really start thinking, instead of jacking compression ratios, start thinking mass. How do I get mass out to my evaporator? So we'll follow the discharge line. We're going to have the same type of setup as a synthetic design as everyone's always worked with, pressure differential valve here. Okay. And then after that pressure differential valve, we're going to inject into the medium temperature suction header. So we're going to create a pressure differential across that valve, minimum of 20 psi to a maximum of 40. And what I mean by that, it all goes back to where your evaporators are placed. So we have never done a project above 40 psi pressure differential. and we've never done a project lower than 20. So typically, you know, as with synthetics, we're always around 20 to 25 psi for a pressure differential for our hot gas valve, okay? And then we just go into a hot gas manifold, and here are my hot gas solenoids, pretty standard setup, and those are going out to my evaporator via the suction line. So what we're going to see here is a few things that are slightly different that we're going to start talking about. Here's the assembly right here. The first thing that you're going to note is we got this discharge header leaving the scroll compressors. And what I'm looking at right here is, here's a project we're currently working on. We have 5 low temperature scrolls. These 5 do not even equate to 21 horsepower. Okay, and we have about a 220 MBH at minus 23. Okay, so remember, the reason for that low horsepower is our compression ratio is fairly low because we are condensing or injecting, you know, that's controlling our head, into the medium temperature suction header, which is right here. And you can see that line. If we follow it all the way down, here's that valve we're talking about, that pressure differential, and we go right into our suction manifold. Now, a few interesting takeaways from this, and I would say this is more live and learn on the booster side. Arneg systems, we've done a lot of experimenting in hot gas defrost using the booster side. And what we found is most success, Trevor, is we build a back pressure. You'll notice this valve, if this machine is 16 feet long, this valve is at the very end of our header. We found by limiting ourselves to where we place our differential valve, created less of a, I guess I could say it was a bit of a nuance in the overall back pressure by placing that valve at the very end of the header, extending the header. So imagine all your circuits are right here. So what I'm pointing to is a very long hot gas manifold with all my circuits leaving to bypass basically into that suction side of my evaporator, and then continuing that header down to the end of the machine. So if that machine is 16 to 18 feet long or even 20 feet long, we're going down to the very tip of that before the flash tank. And that's where we put our valve. And we found that significantly assisted in creating the necessary back pressure inside the circuit to properly defrost and create the differential to have that hot gas return. So that was one interesting.
Okay, perfect. So a couple questions that I have. So with this hot gas defrost, and we didn't go over for a lot of it, you use reverse gas defrost, reverse flow. Is that correct?
That's correct. And I got a slide coming up to show that. Absolutely.
Yeah, no, perfectly, because I jumped ahead there. And so now you have your differential valve at the furthest end. You have all your, I guess you'd be using, are you using CDS valves for the EPR valves, or what valves or type of valves are you using for those?
Yeah, so on the suction side, just like in the synthetic world, it could be a suction stop, a solenoid. Okay. It could be a Belimo. You do that as well.
Yeah.
Or it could be a CDS.
Okay. Excellent.
So we're going into hot gas. We're going to close that suction side down.
Okay. And so for the valve, that differential valve, what options do you guys use for those differential valves?
So it's interesting you mentioned that. We're having a significant amount of, and I want to stress significant, the stability of the valve is very important. It's currently a Danfoss ICMT body with a pilot head on top of it.
Okay. Yeah, because that's the ones I've seen before in the field, and I've heard that people have been having good success with those, and I just wanted to find out from you used.
Yeah, the valve is interconfigurable, so it can be a pressure differential valve or it can be a holdback valve. We use the identical valve in, say, heat reclaim applications as a holdback. So it's nice that it's one convenient package. Now, that being said, it's not just Danfoss that creates these types of valves. There's a lot of different valves. We're doing a few tests with like the other valves, and even on the transcritical side, we use like a pressure differential valve where we can reduce that pressure and do more of a latent heat of vaporization defrost, right? But on the booster side, this is really what we like. It's a Danfoss ICMT body, has a pilot on it, has a solenoid on it. And if you notice here, we couple that with a solenoid.
Yeah.
And that solenoid opens at the very end of the defrost to relieve any type of back pressure, so the CDS stays seated.
So that,
And that was an
sorry, Philip. So that valve, the Danfoss valve, that one keeps a differential when something goes in defrost. Is that correct?
that's correct.
So
Yeah.
when nothing's in defrost at that point, that is a full flow. Is it valve?
That's a full flow. That's a full flow valve. But what we found is maintaining a 20 to 40 pound pressure differential at the very end of the defrost, and we're going into drip time. The solenoids could shatter depending on the entire circuit. So what we do is, similar to in synthetic design, we add a solenoid in parallel to the Danfoss pressure differential valve, and we just open that, and it relieves all back pressure.
So
The
then that
entire
would reduce
system.
that chattering you were talking about potential that could happen?
That's right, because the electronic valves could unseat themselves at the end of a defrost, and it's a simple relief of back pressure. It was a simple solenoid you put in, and the control system quickly opens that for 10 seconds, and it just relieves the back pressure in the entire system, and all solenoids and all valves stay seated.
Excellent. Yeah, no, that makes sense.
It's not just to point that out, it is not an inefficiency in the system. We do that on a high mass system. So when I say high mass, the system you guys are looking at right now is 23,000 pounds per hour. It's a lot of mass going through this system, right? So a small mass system for us is anything below 5,000 pounds. So say 5,000 pounds, nowhere, we're not adding any type of solenoid to relieve back pressure, but higher mass systems we do, absolutely.
And because I really want to get into the amount of mass that you need, because this is a big question a lot of people have. Because if you have, the more cases you have, the more mass the more defrost you're going to need. And this is where I heard people like, okay, I need a 60-minute defrost instead of my usual 40 or 30-minute because I got more evaporator to defrost. And I'd love to get into understanding how to reduce that amount of time, because that's what you said earlier. That's what technicians are doing. I talked to them. I did it for an hour and 10 minutes now to defrost, where it used to be 45 minutes or 18 minutes or 20 minutes with an HFC system, but they just don't understand that you need the more mass in these low booster hot gas defrosts.
Yeah, so the key secret going into a supermarket application, and I'll stress supermarket because we're dealing with case lineups. Industrial is a bit different because we have we have a much different application. It's one larger evaporator. So supermarket hot gas, using the booster side being the subcritical application, it's mass. Temperature 160 degrees or 150 degrees is adequate to defrost your coil. The idea is proper pipe sizing in order to give that mass to the system. And there's a trick in doing that. Back pressure, as we just spoke about here, makes a lot of sense, right? So let's ensure that we have that proper pressure differential. Let's ensure that our bypass for what we spoke about over here, my hot gas header is adequate enough, because remember the pipe sizing is smaller in CO2, right? So we got to really work on a sense of velocity, mass being delivered to the case in a 1/2 inch or 5/8 pipe suction side. The synthetic world, we're running with minimum 7/8 on a suction side in supermarket, right up to a 1-in-1. Yeah. So the quantity is completely different than a CO2.
So does that mean it has to be piped differently? Because this is what I heard. Well, we have both 5/8 coming to the case and leaving the case, and now we got hot gas, and we ran into issues where we had to run longer defrost times to get it from that side.
No, not. Yeah, we've heard that. We've heard these types of. Well, we've had these types of questions, and we've heard about these in the industry. Absolutely not. And what we're going to talk about is a few of those tricks with your evaporator and how it's set up to ensure that you get that mass through the evaporator adequately. And in terms of CO2, we got to be conscientious as well. We can't overdo it. So I'll give a few rule of thumbs that we work. Like if you're doing a bunch of doors, so you're working in a supermarket and you have a bunch of doors, I wouldn't exceed 20 doors for a defrost. A 20 door lineup is probably the maximum you want to do on your hot gas defrost circuit. Islands, adding 3 islands, at least for us, 3 wide islands, we wouldn't recommend. We will go 2 islands, to adequately get that heat out of there and into the evaporator for proper defrosting from inside the evaporator. And we have the availability of working with Arneg as well. Arneg Canada is basically our sister company, and we do significant testing with them. So understand the type of case, the type of coil that's being used as well is extremely resourceful. So our applications we're looking at, it's copper piping, aluminum, maximum 20 doors on that defrost lineup, 2 islands. Take into consideration when you're doing your pipe sizing, and in a third session, I'd be happy to go through that. Not only look at your liquid velocities, but look at your hot gas mass through the system. And there's a way of doing that. There's software out there. You can take a look at your mass flow moving through that system. And then pressure differential. On a circuit that's in hot gas for CO2, it is normal to have anywhere between an 8 to 20 pound pressure differential from hot gas manifold to the returning hot gas manifold. And I know in the synthetic world that seems a bit high, but remember CO2, we're operating slightly differently. So if you do have that larger pressure differential between the 2 manifolds, it's really, really normal. Anyway, we've seen 8 on a lower system to 20, where you're dumping 1,400 pounds an hour into a circuit. Okay.
Yeah. Awesome. I hope everyone's taking notes, because this stuff is key.
So here's a courtesy of our friends at RefPlus. We do a lot of work with this with RefPlus, and I just wanted to go through the reverse cycle. So as Trevor mentioned, we are talking about reverse hot gas cycle. Typical, we call it the supermarket cycle. So we're entering here in the suction line. Remember, we have a drain pan heater as well. So most applications, we're going to heat the drain pan before we get to the evaporator. We can't forget that. We want all that heat to get out in the drain pan, get that moisture going down, that condensate going down the drain line. And then as our drain pan's warming up, we're going to have a higher quality of heat getting out into our evaporator. So let's follow that train of thought, and then let's see how we can improve this. So here's our suction line right here. Our defrost is coming down. We're going to hit our check valve right here. So our hot gas is going to go through the drain pan, back up, and then through our evaporator. Now, we just spoke about CO2 in mass, and mass is critical. We hit our TXV, and we're going to go through this check valve. And that, in our opinion, was satisfactory for our synthetic days. But CO2, if it's about mass, and all these TXVs are electronic, we open them. Relieve the mass, that's the blockage here. What you want is a greater velocity continuously moving through your evaporator. The roadblock here is your TXV. In most applications, there'll be a option that you can open your electronic TXV throughout hot gas defrost. Now, we're not oversizing TXVs. Our strategy is the TXVs is sized normally, and we'll open that throughout a hot gas defrost and let that mass pass.
Oh, that's interesting, because I've not heard of that before. That's pretty cool. So you keep it the same size. If it's a 2-ton coil, you'll keep it a 2-ton EEV, for example, or whatever it is, and then you'll just open that. So it'll go through the check valve, but it'll also go through the EEV at the same time.
You got her. Absolutely. And what we're doing is we're allowing a greater amount of mass to move through that evaporator. And strangely enough, most control platforms are already set up. The control platforms that exist on the market that have hot gas are already set up to allow that. So here in Canada, we work a lot with microthermal. It's a common option just in microthermal. In this, by all means, I don't want to make it seem like this is just relative to Arneg. some of the pioneers in North America for hot gas defrost was doing this way back in 2008, 2009. And I believe as we fine-tuned hot gas, we may have lost some of that. But if you're working on with a microthermal system or a system that allows you to do that, and you're struggling with some defrost times, before trying to obtain greater amount of heat from your booster side, try opening up your TXV, and I think you're going to be surprised on how that helps bring mass through from the manifold, that's your hot gas manifold, down through the evaporator and back. Okay? Because once again, we're talking not only temperature, but mass.
Yeah, because when you open that EEV 100%, you just say you have a 5/8 line there, plus you have that 5/8 going around it with the check valve, and that's giving it the more mass to move, right?
You got her. So this is going to help. This is your metering device on the refrigeration side. But picture this right here. Until we hit these metering devices here, there's no other roadblock in the entire hot gas circuit, realistically, right? If thinking, theoretically, this is what's going to start to control how much you meter back to the hot gas return header. So if we're all about mass, it's trying to alleviate that. Another interesting point to make is hot gas defrosts. Make sure that we have our expansion loops every 100 feet. That, for us at least, that hasn't changed between the refrigerants and now working with the naturals. We really like to see that expansion loop every 100 feet. Most supermarkets, we have enough turns, between rack and circuit that we get our expansion loops in. But it's definitely something. This piping will move throughout hot gas defrost. We got a lot of expansion and contraction. So if you're doing a straight run and you hit 100 feet, we really recommend that expansion loop.
Yeah, and you'll see that in any rack manual. Like any manufacturer is going to say that because that's important with hot gas, and I've seen it in so many different books. And thanks for pointing that out.
Yeah, absolutely. So here's a blow-up picture of one of our evaporators, and I think this is great. It speaks. We got to remember too, there's no distributor for this type of design. The CO2, we removed the distributors. We got limited pressure drop, going directly into that evaporator. So as we're coming back out, here's a liquid line. This one was drawn with a liquid line solenoid. Here's my TXV. Here's my check valve. And you see, there's my bypass for my hot gas. Now, if my liquid line solenoid and my TXV in this application are open, I'm just going to pass hot gas through there. Okay. The interesting thing about this is this strategy, and if I have my liquid line solenoid or my dump solenoid on my circuit, if I have a lineup and say I got 3 or 4 cases, if I obtain my temperature in one of those cases, I just close my solenoid down right here, right? And then I can reroute my hot gas to those other circuits. So best practices using, your manifold style in behind the cases always makes a lot of sense on long case runs, so you can accumulate some of that hot gas and distribute it in an equal proportion. I totally understand it is not always accessible to do that. Every case offers its own different challenges and piping challenges, but anything that in the field we can do to help distribute that hot gas, between all the cases on the circuit in an adequate fashion makes a lot of sense. Adding dump solenoids, now, all due honesty, this is not something we always do, but in this drawing that's here, adding dump solenoids where we can close off the solenoid to help reroute the hot gas, even on the suction side, is definitely something that is feasible in a case, in evaporator setup.
Okay, so for example, if you had 20 doors, say five glass doors per thing, so you get four cases. That dump solenoid, you hit your termination, it's going to close that one off while the other 3 continue to defrost. Is that correct?
Yeah, and then there's going to be so we have in this drawing, there's a solenoid here on the liquid line, and then don't forget so your dump solenoid would be on, I should have specified that, on your suction side. So then we close right down on the suction side, and then we can divert gas into your other cases.
Yeah. Another question, does Arneg, because I've had this conversation with some techs a few weeks ago where, one manufacturer says that they need to come in from one end and do 4, say to 20 doors. Do you guys recommend coming up the middle of the lineup when you're doing for flow, mass flow in the CO2, and then distributing from the middle, or does it matter if it comes from one end or the other and piping?
Yeah, so it's all piping, right? So coming in from one end, you start from one end, and then if you have a 5/8 line, and then you carry that 5/8 line in behind the cases. Let's say that's your suction line, your 5/8 line, and you're just breaking off your 3/8 line to connect to the cases. That 5/8 is acting as your hot gas header at that moment. Absolutely fine to hit it that way.
Okay.
And then if you have your dump solenoids on your suction side, then you're just really waiting to terminate defrost based upon your case temperature at 50 degrees Fahrenheit. And as you shut those solenoids down, then you're just diverting more gas or more mass at this moment to the remaining cases on that line, on that circuit.
Yeah, beautiful.
So whether you come in on the left, the right, or the middle, for us, it's really, I guess it's a rule of thumb with us is carry that suction pipe through, right, to the, and need be, if you're doing two wide islands and you have like a 20-foot space in between, it's quite likely you'll take that 5/8 and maybe step it down because maybe that's what your suction side is. And we're going to want you to do that because it's going to help with that hot gas velocity as well.
Yeah, totally makes sense.
So what we're seeing right now, and I know this might shock a few people, these little tricks that we just spoke about, we're doing 20-door ice cream in about 22 minutes with a 5-minute drip time. So, which is really satisfactory for our clientele. All the little tricks we spoke about here, and then proper pipe sizing is a key feature to this. We can start getting those longer defrost times associated with CO2 down slightly more. And that's where we're sitting. Medium temperature, we're doing medium temperature meat cases in about 16, 17 minutes with a 3 to 5 minute drip time. But ice cream is basically where we're at right now. About 22 minutes with a 5-minute drip time.
And this is using booster hot gas defrost. It's not using.
This is
Yep. Just so everybody
transcritical
knows,
side.
because when you talk about hot gas, and when I always talk about it, it's like, oh, you got the hottest discharge temperature, but when CO2, you get different temperatures from different locations, and this is it's good to know that even though you have this lower discharge temperature for hot gas, you still defrost in 22 minutes. But
Yeah.
it'll be size right.
So pipe sizing is critical. So, and that's more on rack manufacturer. So going into this, we have to accordingly plan hot gas manifold, return manifold, which we're going to speak about right now, because these are all crucial things for mass movement, right? If we ourselves start creating restrictions, then we're never going to succeed in the field. The whole package has to come together. So mass, pipe sizing, and return. I would say return is the most crucial part, because right now we're just throwing gas out there. And gas at a minus 25 coil wants to migrate down into the case. It's one of the coldest points into the circuit. We got this gas at 150 degrees, 8 to 1,400 pounds per hour. It's going to migrate down. But I got to pull that back right now. We got to pull that back into an efficient manner that it complements the design. And this is something different Arneg does. And this is one of our patents. So the hot gas, here's a slide. We kind of piece this all together. Here's our scrolls on the very bottom we spoke about. Here's that discharge header, right? At 150, 160 degrees. Here's my hot gas manifold. This is my supply manifold. All the circuits are leaving from this manifold going down to the case. There's my pressure differential with a relief solenoid. Now here's my return header. And you're going to note this return header goes right back into the flash tank. This is crucial. The flash tank, remember, in transcritical, or even through the whole life of that machine, that tank is basically our condenser. And the pressure differential we're creating is between flash tank and evaporator. The gas coming back from my low temperature side is very, very close to a liquid. I want it to condense inside my flash tank, become a liquid. And that's a condensation that just occurred without ever touching the transcritical cycle. So it's an efficiency gain. I'm using I'm using a resource existing in the system, not only to help defrost the coil, but we're also producing liquid at the very end of that cycle.
So that's a question I have. So when it's coming back, it really should be liquid. If it's coming back and it's not, like, because it can come back, I guess, as a saturated gas, like a little bit of vapor and a liquid. But if it's coming back as a gas, what could be the issue?
Yeah, so if it's coming back as a full-blown gas, I would check pipe sizing, could be an issue. It's typically not going, if things are all set up accordingly, the gas should come back at a fairly good velocity, right? Because we also have that 20-pound, say 8 to 20-pound pressure differential existing in the system. So remember, mass, velocity, pipe sizing, really crucial things in this type of design. We don't want it at this point with this type of design coming back as a full liquid. You just said the key word. We want it coming back as a saturated. We want a saturated gas so we condense inside the flash tank, because it takes a lot more energy to move liquid than it does a vapor, right? So if we're condensing at a too early point and I got a suction riser filled with liquid, it could be problematic, and we're gonna have to use a lot more force to get that back. So hence the pressure differential. But if things are set accordingly, pipe size is done right, my TXV is open, I'll be coming back very, very close to saturation. I will condense inside the tank here and I will become a liquid. So it's an efficiency gain in the entire system.
Yeah. One thing about it, and I'm sure the defrost strategy doesn't change from synthetic refrigerant to CO2, but what is the maximum percentage you would want the store to be in defrost? Like a lot of people say it's 10%, 30%, you know, you don't want more than 40% or 50%, depending on who you talk to. But what is your guys' recommended strategies that technicians should start out with for the maximum defrost at one time?
So defrost schedule, rule of thumb, small application, one case at a time, like one lineup, right? One circuit at a time. Larger mass application, like you have here, we could do 2 circuits at a time. I wouldn't go beyond that. So I've never related to it as a percentage, but in terms of an Arneg system rack with hot gas defrost using the low temperature subcritical side, if we're really under that 8,000 pounds per hour, there's not significant lineup or like say evaporator capacity within that store. Do one lineup or one circuit at the time. Larger, when I speak larger, we're getting into more of the 30, 40 systems. So independently do them 2 to 3 times a day. It's going to be impossible. That larger type of mass system, we can do up to 2 simultaneously.
Okay. Yeah, that makes sense. That's similar to the synthetic. So the strategy, for sure, defrost strategy is very important, and I think this is where people lose their defrosting because they're defrosting too much at once, and it comes back to setting that up.
Well, I would say the common hiccup that we typically see on a CO2 side is you'll have 2 defrosts independently being activated. What I'd recommend, even on the synthetic world from when I was on the tools, is start your first defrost, you know, and then 5 minutes or 6 minutes afterwards, start your second defrost. What you're allowing to do is you're allowing the pressure to equalize in that one system. If we're opening up just valves and we've already pumped out those 2 circuits, right? We're just throwing open hot gas valves open. We're just throwing gas down in there, and then we got to equalize and balance naturally those 2 circuits. I'd recommend start with one. If you have an overlapping defrost, then start the other one. Strategically do that, so you always have a good quality of gas being delivered, right? If you're starting 2 at the same time, there's a risk involved that one of them is going to not have the quality of gas that you want for that defrost, because honestly, the gas is going to take the route the simplest, right? And you're going to probably dump more gas down one circuit and starve the other circuit temporarily. So stagger your defrost. Try, if you have a smaller system, just do 1 independent defrost at a time. If you're going to do 2 at a time, I would recommend never mix cold box or freezer with cases. I'd recommend to, keep your strategy separate. The defrost times, you have one sitting in a sales floor that's going to have an impact from the sales environment. So we have humidity, moisture migration, all those types of things that we have to deal with from the sales floor. Cold box, we have different challenges, right? And unoccupied periods, cold boxes are pretty easy to defrost. They're buttoned up, they're at temperature. Doors, here's an interesting, this is a very common discussion we have right now. So display case manufacturers are moving very aggressively into more of an optimized environment. So evaporator temperatures are rising right now. Doors are being put onto the cases. So if we have a meat case with an evaporator temperature of 30 degrees, it just means this flash tank is going to have to run at a slightly higher pressure, right? Because my temperature of my liquid needs to increase to create that pressure differential for all my valves. But the doors right now, we're straying away from using any type of booster hot gas defrost. So what we're having in some of the new supermarkets is all the low temp on hot gas defrost. Then the medium temp with now the doors is common to be in just off time circuits. So your evaporator temperature is running much warmer. Your delta T's on your evaporators are much tighter. So adding hot gas into that type of environment, it's just unwarranted. It's not required.
Okay, yeah, no, that's good to know. So when we get back to the defrost here, we get the flow, we get the return coming back, we size it properly. We talked last time about flash tank stability. What is happening now? Now I got all this like saturated gas coming back. What is going on with my flash gas bypass valve now at this point when I get all this going on? Because there has to be a good control system to be in place when all this happens, because there's a lot of moving parts at this point. We got discharge
Absolutely.
gas going through the through the CDS or suction stop, through the EEV and the solenoid or the check valve, and then back into the flash tank with your differential valve as well. So now we got a bunch of moving parts. So what's going on with the flash tank at this point?
Yeah, so if this gas is coming back and condensing inside here, naturally by density, that liquid's going to start drop. That gas is going to start to accumulate on the top of the tank. This valve is going to start to open, okay? And we're going to start bringing that down now into our medium temperature header. On a high mass system, what we do to help with that efficiency, it's almost like we do with the booster or the condensing unit application. We'll put, prior to the valve, a flash gas subcooler. So if we're producing a lot of flash gas naturally in the system because of the high pressure expansion device. Here, let me just dig up the picture. This valve right here. And then we got hot gas coming back. Large percentage of it is condensing, becoming liquid, improving the efficiency of the system. But we're also producing that additional gas inside the tank. So this valve is going to start to open. Now, to limit the amount of gas that we're going to send down to our medium temp suction header, we add a flash gas subcooling coil where we subcool that flash gas into a liquid, and we drop that right into the liquid header. And it helps balance some of that inefficiency that could be created.
Okay, so that makes sense. So now what is the difference? How is that valve working when it's 110 degrees outside or in the middle of the winter when it's minus 35? Does anything change, or because I know
go ahead. Sorry, Trevor.
Yeah, because I know if we're talking about the medium temperature side or transcritical side, there's a lot of less heat in the middle of the winter than in the summer.
Mm-hmm.
So, but we're talking about the low side, the booster size hot gas defrost. What is the difference between the middle of the summer defrosting and the middle of the winter defrosting?
So the interesting thing on the booster side is it's not as variant to the ambient temperature as the transcritical side. So as the machine moves into subcritical, the booster is still discharging into the medium temperature suction header. So our compression ratio year round is fairly constant. So you're always going to get between that 150 to 160 degree Fahrenheit. Now, as the heat decreases in the amount of system, mass flow and our net refrigeration effect is changing the amount of compressors that we need to satisfy all that heat, because remember, they say like a wide island, the amount of heat impacting or infiltrating into that wide island in wintertime when store dew point is extremely low as compared to summer makes a significant impact in the overall operation. So you can, the quality of gas doesn't change. And that's why we get back to sizing your piping and sizing the system on mass, right? So we're not going to size a whole system on the whole entire mass flow of the low temperature side right here. Typical hot gas defrost design, we're going to size mass on the first two compressors right here, compressor 1 and compressor 2. Because in a booster application, 2 compressors will run annually on a system like this. These other 3 that you're seeing in the photo will go off. So when we're saying, hey, we're going to size mass, we're going to take a look at these first two compressors and we're going to size around that. Okay, back to the valve, there's significant changes. And we spoke about that last time, if you recall, the changes between the summer and the winter season, especially in Canada. Something we do is this instability of the flash tank can be easily created throughout the winter months. It's more than just saying what's occurring with our flash gas or our gas cooler outlet. Very cold flash cooler outlet or very low pressure in the CO2 system will create instability. Something that we have to take a look at is not only the subcooling coil here to help stabilize this, we actually heat the outlet of the gas cooler outlet as well. If we start falling below 60 degrees Fahrenheit, we'll apply some heat to the gas cooler outlet to bring it up, because we're getting into an environment that just can create instability. These valves, as we were talking about in this drawing, there's one valve, but most applications that we install in Canada or in very cool climates, such as Quebec or Ontario, where Trevor, you and I are from, we'll put a valve for the summer season and a valve for the winter season. To your point, the valve in the winter season is significantly smaller. It is there to handle mass flow throughout the winter months. So the whole goal of all what we're speaking about is the flash tank doesn't lose its stability. We never go into an unstable mode throughout the change of the seasons that we see, such as in Canada, where we have to live through 4 seasons. And that the quality of gas and quality of mass is being delivered to the evaporator by the points that we just spoke about doesn't change. We still want to deliver that mass, whether it be 800 pounds per minute going down into the circuit at 150 to 160 degrees Fahrenheit. It's just, we're not going to size that whole low temperature system. If I got a circuit at 3,200 pounds per hour, I'm not going to say I have that 3,200 pounds per hour for my entire mass flow. It would be a bit unwarranted as well in terms of engineering design. But we'll be realistic and say, if I'm using my low temperature booster side, I'm going to size my hot gas defrost on those compressors that are going to run annually. Okay.
Yeah, totally makes sense. That's super cool. And just for the people who are listening, you're using a plate heat exchanger to heat that gas outlet from the gas cooler, right? To heat up.
Yeah. So it's interesting. This this plate heat exchanger you see here for subcooling, we will couple it with distilled water or glycol. It could be provided by the customer for a hydronic loop they have, or it could be independent where it's hooked up maybe to like a small CO2 condensing unit or propane unit that has a plate heat exchanger, and we cool the glycol to help do some subcooling. The opposite effect in winter need be if we start to lose temperature from the gas cooler, we'll run that fluid through there to help bring it up to about a 70, 72 degree Fahrenheit gas cooler outlet.
Awesome. Yeah.
We have in Canada, I think I know there's a lot of folks on this call. So just to paint a picture, we have applications, right? Like right now in Edmonton, where we're going to see minus 38 degrees Celsius.
That's on a warm day.
Yeah, with high winds, typical in Montreal, I presented this at Atmo and I had a lot of interesting emails on it. We'll see I'll give you in Fahrenheit, we'll see minus 30 degree Fahrenheit up to plus 95 degree Fahrenheit, you know, throughout the summer. And any given day could be as low as the morning is 20 degree Fahrenheit, and we will easily climb to 82 degree Fahrenheit by mid-afternoon, or 88 degree Fahrenheit as well. So the variation, if not properly accounted for in the engineering, creates significant instability. Trevor, getting back to what you said, another point, high mass systems, because the amount of liquid we have to store, we'll actually add a second flash tank. And picture it as like an intermediate pressure vessel where in the winter months, we just dump liquid into that secondary flash tank because we're running at like 10% capacity.
Awesome. Yeah, it makes sense too. And like, there's a lot of people listening, and more people will listen to this. It may sound complicated right now, but if you take your time and go through each system, if you're working on an Arneg system, start from the compressors, follow the piping, have the P&ID diagram with you, and walk through each section. If you're doing the defrost section, just take the defrost section and walk through to find each valve. What's this valve do? This is the differential valve. Here's the solenoid valve, and do it step by step. And you don't have to learn this overnight. You just need to take your time,
Yeah.
learn it over time.
Well, the interesting thing is, as you can see here, this looks pretty typical to what we've all worked on over the last 20 years. The only thing is now my hot gas, at least in our design, now that hot gas manifold is just stretched out to the end of the rack, right? But I still got my pressure differential. You know, we've always done it on the discharge line after the oil separator. Well, and then we would bring our hot gas back and dump it into the manifold, or directly into manifold prior to the condenser, or directly up to the condenser. Well, instead of doing that, my flash tank, I'm considering it now as that condenser.
Yeah.
So here's my pressure differential. I'm dumping it into that suction manifold because that's what's controlling my compression ratio. So theoretically, my setup hasn't changed. The way we're doing the piping in order to make it work, because it's a booster system, has changed, right?
Yeah.
And the circuit layout is identical. Like, you still got hot gas solenoids, there's still the check valves, you still have CDS or suction stops closing down, we're going into a hot gas setup. So all that to the eye hasn't changed whatsoever. I'd say the biggest change is just saying, wow, that flash tank, I'm returning to it. It's really crucial for me to understand where that pressure is on the flash tank, because as I change that pressure in the flash tank, it changes my pressure differential on my valve. And I'm injecting into my manifold. So as I change my suction as I change my suction pressure, it's going to impact my hot gas. These are the things we just got to start thinking about, right? Like, hey, I want to drive the suction slightly cooler to overcome a certain circumstance within the store. Just be aware that that is going to impact your hot gas and everything else we spoke about. So once we get over those little nuances, the idea of the setup is very, very similar to a synthetic design.
I love that. And I do have a question too, because now we're using lower discharge temperature. A lot of people are worried about, well, there's so much thermal shock with hot gas. There's a potential for leaks because of the changing temperature. What is your thoughts on this low booster system hot gas with thermal shock to the piping?
Yeah, so once again, so thermal shock is going to occur when we do what? We're going to create sublimation, basically, right? We're going to mix liquid and something hot, and we're going to vaporize immediately. We're going to create a shock. So a few things. Do your pump out, okay? And we're not delivering 200 or 250 degree Fahrenheit down into the display case. So what's really interesting is the 150 to 160, and now dependent upon mass, so the 150, 160 degree Fahrenheit dependent on mass, we've measured in our lab, like the contraction and expansion of the piping is a lot less. If you take a look at we've done a lot of interesting testing with some of the new synthetics, and they burn hot. Like in a hot day, we're seeing high pressures. So like 448A, we're coming off of 210 to 230 degrees Fahrenheit, and we're running like 220 to 250 PSIA when it's like 38 degrees Celsius outside. We're not going to see that here. So what we've noticed is the contraction and expansion of the piping is a lot less. Still recommending those expansion loops, okay? But still pumping out. We don't want to be injecting hot gas into an evaporator full of liquid still. Still close it down, still pump out your circuit, and then open up your hot gas valve and come on and let that hot gas migrate down at a good velocity, go through your evaporator, and then properly come back into your flash tank.
Are all these set points for your CO2 cases, because you guys manufacture lots of cases, would all these set points be in your manuals to start off, like for the pump out, for the drip time, for the defrost recommendation? Would that be in your manuals?
So it's not in the manual. So we write the specifications on a per project basis. So every machine that Arneg system produces with the complementary Arneg cases, we do all the programming. So it's based upon that project that we produce the documentation and literature, because all honesty, based upon pipe length and pipe sizing, we'll fine tune those times that we feel are adequate to achieve the hot gas defrost.
Yeah.
So once again, we get back down to that 20-pound to 40-pound pressure differential, right? We'll fine tune that and give those recommendations, and we will provide that in a documented way that's clearly outlined and set up already in the existing control system for the technician on the job site.
That is awesome. That is awesome. I love hearing that. We are getting to time here. We do have a few questions I'd like to ask you. So, in the case of a CO2 walk-in freezer evaporator, is it possible to use hot gas defrost?
Yeah, absolutely. We do that all the time. And there's two strategies in that. That's an interesting question. And our customers are really divided on this. And it becomes a personal choice. We have customers that will use hot gas defrost on everything in the store, including the produce, because their defrost time, they say, is a lot less, and they feel it's better product integrity. The walk-in boxes, we have customers that leave the fans running for certain walk-in boxes throughout a defrost. So if it's a high temperature box, we have customers say, leave the fans on. They won't turn the fans off throughout a hot gas defrost. They feel it speeds up the time, whereas we have customers on the opposite direction that we shut all the fans off.
And that's in the medium,
so that is
like the high temperature, the medium temp boxes.
You got it.
The low temp.
Like a produce box.
Yeah.
Fruit cooler produce box.
Yeah.
They say the additional humidity in the air, it's not bad for the product, because a lot of the leafy greens or whatnot is basically 90 to 98% water, right? So we have customers divided on that two areas. But yes, to answer the question, hot gas is adequate for the freezers and the medium temp coolers.
Awesome. I think we answered this one. Is an EEV open during defrost, and you guys do that? You'll open it 100% for back pressure to have more flow. Is that correct?
We recommend that. That's correct. Yeah.
Okay. And then the last one, can you elaborate on your 5-minute drip time? What is your process for your drip time?
So at the termination of the defrost, we want a drip time for the drain pan, whether it be case or an evaporator in the walk-in box. 5 minutes is our starting point. What we want to do is we want to ensure all that condensate that's at the bottom of the drain pan is now properly into the pipe. Any type of condensate that's left in the drain pan, and then when you go into refrigeration once again, will freeze and naturally become problematic. So a good starting point we find is 5 minutes. Extreme cold applications, we do applications down to -34, may need a slightly longer drip time, where typically we're going to see 7 to 8 minutes drip time and something like that.
Awesome. Phillip, this has been amazing. Where can people find out more about you, more about Arneg, if they want to get a hold of you and your products?
So the last time the folks just hit me through LinkedIn, which is absolutely fine. On LinkedIn, you'll have my email address, so feel free to reach out. Arneg, if you visit our website. Now, we had a lot of folks reach out to say, hey, can we get into that technical resource area? North America is still working on that technical resource area. Our goal is to have that up and running. Give us about 18 months to have that fine-tuned. but that's an area that we're hoping to build for the technicians and give documentation on our racks and training material.
Amazing. Once again, I want to thank you so much, Phillip, for taking the time. I want to thank everyone for joining us. If you found value in this conversation, please like it, share it with your friends, share it with other people so more people can learn about hot gas defrost from low booster side of the system. Thank you, Phillip, and have a fantastic day.
Right on, Trevor. Take care, everybody.
Hey, I want to thank you for taking the time to watch this video. I hope you got something out of it, something that you can use in your daily life. If you like this video, hit the thumbs up button, hit the subscribe button, and click the bell button, because when you do click the bell button, it will notify you anytime new videos are released. Also, check out the Refrigeration Mentor webpage at refrigerationmentor.com, where I'll have all the different trainings, upcoming events, the different podcasts I've been on, as well as the Refrigeration Mentor podcast. If you want to check that out on Apple, Spotify, Google, any service provider of your choice. Super excited to see you at the next video. Now let's get a conversation going.